All right, let's talk about a piece of tech you've almost certainly used, maybe even this morning, without ever really thinking about it. It's called fuzzy systems, and it's all about making our machines think a little less like a calculator and a whole lot more like, well, us.
I mean, it all kind of starts with this question, right? You've seen that label, fuzzy logic. It sounds, I don't know, a little vague, maybe just some marketing buzzword. But it's actually a huge clue to a completely different way of thinking about computation. So to really get it, let's think about two things. On one hand, you've got traditional computers. They use what we call crisp logic. It's like a light switch. It's either on or off, 0 or 1, true or false, there's nothing in between. But fuzzy thinking? That's way more like a dimmer switch. It's not just on or off, it can be dim, or maybe bright, or even brilliant. It totally embraces all those shades of gray in the middle.
And that really is our first big idea here. We're moving beyond a world of simple, true, or false. Fuzzy systems are built from the ground up to handle all the ambiguity and uncertainty that's just, part of the real world.
So the crucial point is this. Fuzzy logic lets us translate these kind of vague human ideas, like somewhat warm or very dirty, into a language that machines can actually work with. So instead of needing a super precise temperature reading, like 25.3 degrees, a fuzzy system is totally cool with just the general idea of warm.
Okay, so how do they pull this off? How does a machine actually think in this fuzzy kind of way? Let's pop the hood and break down the mechanics.
Now, this diagram might look a little complicated, but don't worry, it's really just our roadmap. A fuzzy system has three key stages. First, you've got fuzzification. This is where you take a precise number, like a temperature from a sensor, and you turn it into those fuzzy ideas like cold or warm. In the middle, you have the inference engine. That's the brain of the whole operation, making decisions based on a set of rules. And finally, you have defuzzification, which is where you take that fuzzy decision and turn it back into a concrete, specific action, like setting a fan to exactly 75% speed.
The real magic starts right here with something called membership functions. This is the key idea. A specific temperature, let's say 18 degrees, isn't just cold or not cold. Nope. It might be, say, 80% cold, but also 20% warm at the same time. These functions, whether they're shaped like triangles or smooth curves, are what define those all-important shades of gray. So once we have our fuzzy concepts, we need some rules. And this is where it gets brilliantly simple. They're just basic if-then statements, the kind of thing you could write in plain English. For example, if the dirt level is high and the fabric type is delicate, then the wash time should be long. This is the system's entire knowledge base, right there. Now let's get to the brain of the operation, the fuzzy inference engine. This is the part that takes all those simple rules and evaluates them all at once. It looks at the fuzzy inputs, like the clothes are somewhat dirty. It weighs all the relevant if-then rules, and it combines all their outputs to come up with a final fuzzy conclusion. Something like, the wash time should be medium to long.
All right, now that we've got a handle on the how, let's look at the where. Where are these systems actually out in the real world, making a difference?
Building one of these isn't black magic. It's a real structured engineering process. You start by figuring out the problem and defining your variables. Then you create those membership functions and rules we just talked about. And finally, you pick your methods and test the whole thing to make sure it actually works like you expect it to.
But wait, where do those rules even come from? Well, sometimes they come from a human expert who just knows their stuff. But what's really amazing is that they can also be learned automatically. By just analyzing a bunch of data, a system can find patterns and generate its own fuzzy rules, no human required.
Generally speaking, fuzzy systems really shine in three big areas. First up, control systems. Think managing an industrial process or even a subway train. Second, pattern recognition, like figuring out someone's handwriting. And third, decision-making, like maybe helping a bank decide whether to approve a loan.
And here is a classic problem that shows this off perfectly. On the left, you've got this incredibly difficult challenge, trying to balance a pole on a moving cart. It's super unstable. And on the right, that's the fuzzy solution. That grid is just a map of the rules. Like, if the angle is positive small and the speed is 0, then give the motor a positive small push. It's an incredibly intuitive way to solve a really tricky problem. And this isn't just a lab experiment either. The Sendai subway in Japan uses a fuzzy control system to handle its acceleration and braking. And get this, the rules were created by interviewing experienced train drivers. They basically captured that human expertise and intuition to create a smoother, more efficient ride for everyone. When it comes to pattern recognition, fuzzy logic is a lifesaver because it handles variability so well. I mean, think about recognizing a handwritten B. Everybody writes it a little differently, right? A fuzzy system can use rules based on how much the character crosses certain zones, which makes the whole thing way more flexible and reliable. And that brings us right back home to the washing machine. When you see fuzzy logic on that label, it really means something. It means the machine is using sensors and fuzzy rules, probably about how dirty the water is or how heavy the load is, to figure out the perfect wash time, maybe even how much water to use. It's honestly one of the biggest commercial success stories for this entire technology.
So what's the final verdict? When we step back and look at the whole picture, what are the real pros and cons of teaching our machines to embrace this kind of uncertainty?
Well, the advantages are pretty huge. The rules are written in a way humans can actually read, which turns the system from a mysterious black box into a white box. You can actually see how it's thinking. It's modular, so adding or tweaking rules is easy. And of course, its biggest strength is handling the messy, inexact data you find in the real world.
But, it's not a silver bullet. There are definitely some downsides. It can be more computationally expensive. Coming up with a really good set of rules can be a massive challenge. And trying to optimize the system is tricky, because if you change one little membership function, you might have to go back and change all your rules too.
Ultimately, here's the key takeaway. A fuzzy system usually needs way fewer rules than a traditional crisp system. And why is that? It's because each fuzzy rule is so much more expressive. A single rule like if temperature is warm covers a whole bunch of different actual temperatures, which makes the whole system more compact and efficient.
And that leaves us with one last thing to think about. As we build more and more AI to help us navigate this complicated world, maybe the goal shouldn't always be perfect, absolute precision. In a world that is, fundamentally, pretty fuzzy and full of ambiguity, maybe we should be teaching our machines to be just a little less certain too.